Okay guys, so this is time to do another video. So today I'm going to tell you how to find magnetic field near a current carrying wire. It's a long wire. So what am I talking about? What I'm saying is this. Let's suppose you have a wire and then the current is going up. That's the direction of the current. Then I want to find the magnetic field at a point which is a distance, a perpendicular distance r away from the wire. I want to find the magnetic field B. Okay? And the magnitude of the magnetic field is given by this. It's mu 0 I by 2 pi r. Here r is the distance, perpendicular distance from the wire to the point that you are thinking about, and I is the current carrying in the wire, and mu 0 is called permeability of the vacuum, and it is given by 4 pi times 10 to the power negative 7 Tesla meter per ampere. So that's a unit for mu naught. That constant mu naught is a very interesting number because remember we had a similar constant k that we use. K which we use approximately equal to 9 times 10 to the power 9 Newton meter squared per Coulomb squared. Remember that? That K can be also written as 1 by 4 pi epsilon naught, where epsilon is another constant. Together, between these two constants, you can express the velocity of light like this. Velocity of light c is 1 divided by the square root of the product of mu naught and epsilon naught, and it's approximately equal to 3 times 10 to the power 8 meters per second. Okay, so see, these constants have really fundamental nature, right? That they give you this fundamental constant, that velocity of light. Okay, now what about the direction of the magnetic field at this point? Will it be coming out? Will it be going in? And the rule is called the second right-hand rule, right? Or right-hand rule number 2. And it's very simple. I'm going to draw a head here. All you have to do is hold this wire like this. And this is your thumb. Your fingers are coiling around it. That. So if you're holding the wire like that, this is the direction of the current, then the magnetic field will be like your fingers coiling around the wire. So the figures I drew that look straight, but actually the magnetic field will be going around the current carrying wire like this, right? Like a loop. So it'll be like this, right? So just pretend that this is a wire. Then the current is going up in the direction of this red cap. Then what I'm saying is this. Hold the wire like this with the thumb in the direction of the current. Then the magnetic field will be coiling around like your fingers around this wire, right? So in this case, it will be like this. Right? So that's a simple formula, and let's apply it. So exercise example 22.6 tells you that there's a wire and carrying current I, and what I want is the magnetic field B at a point which is 5 centimeters away, perpendicular distance away from the wire. The magnetic field I want is 2 times the magnetic field of the Earth near the surface. Okay? Then what current must I carry so that the magnetic field B at this point will be this much? Alright, so it's no big deal, but we know the magnetic field B near the Earth is 5 times 10 to the power negative 5 Tesla. So then the magnetic field B that we want at this point is 2 times 5 times 10 to the power minus 5 Tesla. Or it's just 10 times 10 to the power negative 5 Tesla. Right? I'll leave it like that. So, according to our formula, B is equal to mu 0 I by 2 pi r. Now, what I want is a current I. So, current I is equal to 2 pi r times magnetic field B divided by mu 0. So now I want is 2 pi, what is R? R is 5 centimeters, but I have to express it in meters, so 10 to the power minus 2 meters. Then I have magnetic field B, which is equal to 10 times 10 to the power negative 5 Tesla. Divided by mu naught, which is this, 4 pi times 10 to the power minus 7 Tesla meter per ampere. So you see that 4 pi and 4 pi, 4 pi and 2 pi, that give you a factor of 2 in the denominator. So that will give you 5 by 2. So let me continue here. So there will be I is equal to 5 by 2. Then 10 to the power negative 2 and 10 to the power negative 5. That's 10 to the power negative 7. And there is 10 to the power negative 7 in the denominator. So 10 to the power negative 2, 10 to the power negative 5, that's 10 to the power negative 7. That is 10 to the power negative 7. They cancel out. Multiply by 10. Meter cancel out, Tesla cancel out. 1 by ampere in the denominator, so that will give you amperes, which is equal to 2.5 times 10 is 25 amperes. Right, so that's example 22.6. Okay? Now, and the next one is I'm going to derive a formula to find the force between two current carrying wires. Okay? So remember, we know how to find the magnetic force on a current carrying wire. That is ILB sine theta, right? We did it in the last lecture. So now, if a wire is carrying current, then now we know that it will produce magnetic field. So if I have two wires carrying current, one guy is carrying current, this guy is carrying current, they will be producing magnetic field, they will be in each other's magnetic field. That means they must be feeling the force from each other, right? They must experience force coming from the magnetic field of the other wire. So how do we derive that? All right, let's do that. So actually it's not difficult. You know all the algebra. We'll do it step by step, all right? So first of all, what I'm going to do is I want to find the direction of the force, okay? So now I'm going to think about a wire, current carrying wire, I1, and there's another guy, current carrying wire, I2, they're carrying current in the same direction. I1 and I2 are not necessarily the same. So now, as I told you, if I have this wire carrying current, then all I have to do is hold the wire like this, and then you see my fingers are coiling around it, the thumb in the direction of the current, so the magnetic field is going into the board, right? So at the point where this wire 2 is there, then the magnetic field is going into the board, right? Because the wire is here, right? So I'm holding it like that, so the magnetic field is going into the board, like my fingers. So I'm going to draw these little crosses. These are the magnetic field coming from wire number 1. So I call it magnetic field B1 in, because that's into the board coming from number 1. Okay? So now, we also know that from the right-hand rule about the current, that if I have magnetic field B in the direction of the palm, going in the direction of the fingers, and this is the current in the direction of the thumb, then the force will be going out of the palm, right? So this is your finger, this is your hand, and these are your little fingers, right? And this is your thumb, and your palm is up, right? So magnetic field B, current I, the force will be going out of your palm. So in this case, the magnetic field B is going in, the thumb is in the direction of the current going up, then the force on the wire must be coming out of my palm like this to the left, you see, towards the other wire. So the force coming from the wire number 1, right? So F acting on 2 coming from 1 will be in that direction. You see that? Okay? Now, what about this guy? Well, this guy also will feel the magnetic force because of the magnetic field from the first wire. So think about this. This guy, the current is going up, so my fingers are going around it. So at this point, where the wire is, the wire number 1 is, my fingers will be coming out of the board. So then I'm going to show the magnetic field with these little dots. That's magnetic field B coming out of the board. Right, so that's B2, that's magnetic field B coming from wire number 2, right, and that'll be out. So now in this case, I have to point my fingers towards you. The thumb is up because of the direction of the current. Then the force will be coming out of my palm, that is in this direction, that is towards the other wire. So the force from this feeling and the force experienced by this wire number 1 will be F on 1 coming from 2 is towards the other wire. So obviously, if the two wires are carrying current in the same direction, then they will attract each other. Okay? So now I will let you practice the other case where the two currents are opposite to each other, then obviously the answer will be they will be repelling each other. So try that, see if it works, right? So first leave this alone, turn this around, and then turn this around, leave this alone, see if you get what you should logically get, that is, they should be repelling, okay? Now, the next step is to find the magnitude of the force. Obviously, the magnitude of F21 and F12 must be the same because of Newton's third law, right? Every action there will be equal and opposite reaction, right, for two objects. So now, let's calculate the force feeling by wire number 2, F2 coming from 1. What is that? Well, we know that. What is the formula? That is I, L, B, sine theta. And I is the I of this guy, so it will be I2. Why? Because the magnetic field is coming from magnetic field of the wire number 1. So this is wire number 2, so that's I2. L is common to both of them, I'll just leave L. B is the magnetic field coming from wire number 1, so I call it B1. The next step, I2 is I2, L is L. What is B1? Well, B1 is, remember, when I have current I, a distance R, at this point, magnetic field B is equal to mu 0 I by 2 pi R. So, I want B1, that is magnetic field coming from wire number 1, that means this current has to be I1. So, B1 is mu 0 I1 by 2 pi R. R is the distance between the two wires. And I put sine theta. Theta is equal to 90 because we take perpendicular. The two wires are parallel, so the magnetic field and the current is perpendicular, so that will be sine 90, that is 1. So now that is just mu 0 I1 I2 by 2 pi R times L. So instead of just finding for a particular length, we'll just find the formula for force per unit length L will be mu 0 I1 I2 by 2 pi R. So that is force per unit length between two current carrying wires. One is carrying current I1 and one is carrying current I2. And the direction, we already found it. If they are in the same direction, currents are in the same direction, the wires will attract. And if the currents are in opposite direction, they will repel. Alright? So that's the formula. Now, there are two little more formulas that I want to tell you, but I cannot derive, because in order to get that, I have to use something called Biot-Savart rule, and then I have to use integral calculus in order to give you the answer. So, actually, a simple one. You just think about a loop, a circular loop. So, current is going in this direction. And then, so it will be going out in that direction. And so, if current is going in that direction, I hold a wire like this. So, then because my thumb is in the direction of the current, so magnetic field will be coming up like this. I'm not drawing very good, but okay. And the magnetic field at the center is given by mu 0 I by 2 R, where R is the radius of that loop. Unfortunately, I cannot derive it, but it's just a formula. Okay? And another one is called a solenoid. You know what a solenoid is? It's just a coil with many, many loops. And the current is going up, current is coming down direction. And then in this case, the magnetic field will be going like this. Going inside the solenoid into the loops, coming out from the other side, right? Okay? And that magnetic field B inside the solenoid B is equal to N mu 0 I. And I is a current. Mu 0 is a constant that we talk about, 4 pi times 10 to the power negative 7 Tesla meter per ampere. And N is the number of loops per unit length. So that's number of loops, not the total loops, per unit length. Okay, so there's an example, I think it's example 22.7. Okay, example 22.7, let me do a quick job on that. And example 22.7 says that you have a solenoid 2 meters long, so it's quite long, a little bit over 6 feet. So example 22.7. So length is equal to 2 meters. It has total number of loops is equal to 2,000. 2,000 loops total. Loop is not a unit, right? It's just a number. But I'm just writing it down. I don't think that this is unit. Loops. And we want to find the magnetic field. So B is equal to N mu 0 I. N is the number of loops per unit length. So N is 2,000 loops pi 2 meters is equal to 1,000 loops per meter. So the unit is per meter. Okay? So now B is equal to 1,000 loops per meter times mu 0 is 4 pi times 10 to the power negative 7 Tesla meter per ampere. And the current I in the problem is I is given as 1600 amperes. So times 1600 amperes. So you can see that Tesla meter and meter cancel out, ampere and ampere cancel out, Tesla is the only one left, and if you multiply it out, the answer is 2.01 Tesla. That's your magnetic field B for that solenoid. Okay? So you can sort of see if your answer is correct. So this 10 to the power 1, 2, 3. So that's 10 to the power 3. This is 1, 2, 3. So 10 to the power 3. So 1.6 times 4 pi. So 1.6 times 4 pi. 10 to the power 3, 10 to the power 3. So that's 10 to the power minus 6. 6, so there's 10 to the minus 7, so that's 10 to the negative 1. You see, so 1.6 times 4 pi is about 12, 3 pi is 3.1, so 4 times 3 is 12, So 12 times 16, and then 10 to the minus 1, so you get about 2 decimals. Okay? So you can mentally check. Because don't trust your calculator all the time, because sometimes you have these little clicking errors, right? Okay? Alright, so we'll quit here for a second.